In this video, we will explain the notion of homogeneous system, the null space of a matrix, and non-singular matrices. Homogeneous means that all b sub i's are zero. And then, as an example, we have the following system, like x1 plus 2x2 minus 3x3 equals 0, 4x2 minus 4x3 equals 0, and 3x2 plus 7x3 equals 0. The solution of this homogeneous system, when we do the augmented matrix, we have 1, 2, negative 3, 0, 0, 4, negative 4, 0, 0, 3, 7, 0. And if we do row reduction, we can check that we end up with this matrix. Which means that in this case, this system is equivalent to the system x1 equals 0, x2 equals 0, and x3 equals 0, which means that the solution in this case is the set 0, 0, 0. Then an important observation is that if we have a homogeneous system, since all the b sub i's are equal to 0, then we can pick all the x equal to 0, and that would be a solution. Then let me write that as a theorem. Theorem: every homogeneous system is consistent. And the reason, actually let me write this as a definition. The reason is that x1 equal to 0, x2 equal to 0, and xn equal to 0 is a solution of a homogeneous system. And by the way, we call this solution 0, 0, 0, which is exactly the same solution, is called the trivial solution. And notice that in general, we always have that this is a solution, but sometimes we have that there are more solutions. In this particular case, for this particular system, we have that the trivial solution is the only solution, but that doesn't have to be the case. But to summarize, every homogeneous system is consistent, and this solution is called the trivial solution. Then if I'm talking about a homogeneous system, and I mentioned the trivial solution, that means the solution where all the x sub I are equal to 0. Let me do another example. Let's find the solution of this system. Then we write the augmented matrix. And the augmented matrix is 1, negative 1, 2, 0, 2, 1, 1, 0, 1, 1, 0, 0. And then we do row reduction. We can see that this is row equivalent to 1, 0, 1, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. Then in this case, we have that this system is equivalent to the system x1 plus x3 equals 0, and x2 minus x3 equals 0, and 0 equals 0. This is what we call a good system. And then here we can decide that the basic variables are x1 and x2, and x3 is free. And then we need to solve for the basic in terms of the free, and then we get that x1 is negative x3 and x2 equal x3. But remember that we need to write the solution set as a vector. Then we have that the solution set is the set negative x3, x3, and here in the place for the free variable, we just write the free variable x3, where x3 is a number. Notice that in the real numbers, then we have that this solution set can be written as x3 times negative 1, 1, 1, such that x3 is a real number. And then in this case, we have that this is a geometrically, this is a line, and the vector negative 1, 1, 1 is a direction vector. And in this case, that line goes through 0, 0, 0. 0, 0, 0 is a point in the line. Okay, then in this particular case, we have that the solution of this system, which we know that it always has a solution, and we always know that it goes through 0, 0, 0, is geometrically aligned, and this is the direction vector of that line. Let's do another example. In this case, the augmented matrix is 2, 1, 7, negative 7, negative 3, 4, negative 5, negative 6, sorry, I'm forgetting the zeros, and here is 1, 1, 4, negative 5, and 0. And we can check that this matrix is row equivalent to the matrix 1, 0, 3, negative 2, 0, 0, 1, 1, negative 3, 0, 0, 0, 0, 0, 0. Therefore, we have that this system of equations is equivalent to the system x1 plus 3x3 minus 2x4 equals 0. And here we have x2 plus x3 minus 3x4 equals 0, and 0 equals 0. Since this is a good system, then we can decide what the basic and good variables are, and then we have that the basic variables are x1 and x2, and the free variables are x3 and x4. And for that reason, we need to solve for the basic in terms of the free, and then we have that right here, we have that x1 is equal to negative 3x3 plus 2x4, and x2 is negative x3 plus 3x4, and then the solution set will look like negative 3x3 plus 2x4, and here is negative x3 plus 3x4, and x3 is free, then I can write x3 here, and x4 is free, then I can write here this, such that x3 and x4 are numbers. In the case that we are thinking that our numbers are the real numbers, we can rewrite this as this, like 0, 0, 0, 0, plus x3 times negative 3, negative 1, 1, 0, plus x4 times 2, 3, 0, 1, such that x3 and x4 are real numbers. And geometrically, since there are two free parameters, this is a plane. And 0, 0, 0, 0, 0, 0, 0 is a point in the plane. And the vectors -3, -1, 1, 0, and 2, 3, 0, 1. These two vectors are the generator vectors. Okay, then as always, since we have an homogeneous system, it is a consistent system because the trivial solution is there, but here we have not only the trivial, but we have more solutions. In this case, the solution set is not only the trivial solution, but it is a plane that goes through the origin in R4. Let me continue with a theorem that is going to be very basic to prove. The theorem says that if you have a system, right, and it is like a1 x1 plus a1 and xn equals 0, and then a m1 x1 plus a mn xn equals 0. If we have a homogeneous system, but n is bigger than m, then what the theorem says is that there are infinitely many solutions. Then let me write down every homogeneous system, with n bigger than m has infinitely many solutions. The reason is that the augmented matrix of this system, which is a11, a1n 0, and here am1, amn 0, this is an m times m plus 1 matrix. And when we do row reduction, then we end up with some pivots. Here, this part doesn't change at all. Then there are some pivot columns. But since there are more columns than rows, you can always pick one column here, not the last one, but there is always one column which doesn't have a pivot. And then this column that doesn't have a pivot, it will go with one variable. And that means that that variable would be a free variable. And for that reason, once you have a free variable, then you have infinitely many solutions. Remember that if you have only one free variable and you are thinking about the real number as your numbers, then the solution of the homogeneous system would be that line. If there are two free variables, then the solution would be a plane, and so on. But this theorem is just the observation that when you write the augmented matrix and you do row reduction to write the equivalent system, you can always find free variables. Then that's the main reason for this theorem to be true. Let me continue with a definition. We are going to define the null space of a matrix. Definition: the null space, and this is what I'm defining, of an m by n matrix A is the set of vectors V such that A times V is the zero vector. Notice that since the dimension of this matrix is n by n, then the dimension of the vectors v must be n by 1. And therefore, if our matrix A is the matrix A11, A1, n, and then AM1, AMN, then the null space, this is important, the null space is just the solution set of the system, of the homogeneous system A11x1 plus A1nxn equals 0, and then AM1x1 plus AMNxn equals 0. Therefore, in order to find the null space of a matrix, we just need to consider the homogeneous system that you get by using that matrix and placing 0 at the end, because it's a homogeneous system, and then the solution set of this system is the null space of a matrix. Let's do an example. If we consider the matrix A equal to 2, -1, 7, -3, -8, 1, 0, 2, 4, 9, 2, 2, -2, -1, +8. Then, in order to find the null space of this matrix, we need to consider the system 2x1 minus x2 plus 7x3 minus 3x4 minus 8x5 equals 0, x1 plus 2x3 plus 4x4 plus 9x5 equals 0, and 2x1 plus 2x2 minus 2x3 minus x4 plus 8x5 equals 0. And then we need to write the augmented matrix. To solve this system, we write the augmented matrix, which is just 2, -1, 7, -3, -8, 0. Which is row equivalent to the matrix and therefore this system is equivalent to the system x1 plus 2x3 plus x5 equals 0, and then x2 minus 3x3 plus 4x5 equals 0, and then here we have x4 plus 2x5 equals 0, which, since this system comes from the row reduced echelon form of this matrix, this is a good system. And then we can define what the basic variables and free variables are. Here we have that the basic variables are x1, x2, and x4. Remember, the basic are the first variables that shows up in each equation once we know that it's a good system. And the free variables are x3 and x5. Then we solve for the basic in terms of the free. Then we have that x4 is -2x5 from here. X2 is 3x3 minus 4x5, and x1 is negative 2x3 minus x5. This means that the solution set can be written as negative 2x3 minus x5, 3x3 minus 4x5, and x3 is a free variable, then I write here x3. x4 is negative 2x5, and x5 is a free variable, then I write x5 here. And then here such that x3 and x5 are numbers. If we are thinking about real numbers, then this can be written as 0, 0, 0, 0, 0 plus x3 times negative 2, 3, 1, 0, 0 plus x5 times negative 1, negative 4, 0, negative 2, and 1, such that x3 and x5 are real numbers, which means that this is a plane, and the generator vectors are the vectors negative 2, 3, 1, 0, 0, and the vector negative 1, negative 4, 0, negative 2, and 1. Notice that in this case, the null space of this matrix is geometrically a plane, and it has infinitely many vectors, and that plane is generated by these two vectors. And another observation is that since we know that we are solving the homogeneous system, somehow we can just disregard this last column, and then we can just consider the reduced echelon form of this matrix and get the answer. But we have to understand very clear that we are doing the row reduced echelon form of this matrix, which is just this matrix without this 0, 0. And then we can set up the system again. Actually, what we just pointed out is that if we want to compute the null space of this matrix, it's the same as computing the null space of this matrix that we have here, which is the reduced echelon form of that. Okay? If two matrices are row equivalent, they have the same null space. Let me do another example. We consider the matrix 2, 1, 0, 0, 2, 1, 0, 1, negative 3. Then, in order to find the null space, we need to solve the homogeneous system 2x1 plus x2 equals 0, 2x2 plus x3 equals 0, and then x2 minus 3x3 equals 0. And then the augmented matrix of this system is the matrix 2, 1, 0, 0, 0, 2, 1, 0, 0, 1, negative 3, 0, which is row equivalent to the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And then this is the augmented matrix of the system x1 equals 0, x2 equals 0, and x3 equals 0, which means that the null space of this matrix, which by the way we denote the null space of A, is just equal to the vector 0, 0, 0. Then geometrically, the null space of this matrix is just a point. Notice that we can have done this by computing the reduced echelon form of this matrix, which is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the null space of this matrix is equal to the solution of this system, which is this. Then we could have done this instead of this. I forgot to mention that if we have a matrix, this is an important thing that maybe I need to emphasize. If this is a matrix, then the null space of A is denoted by n of A. Then this is going to be an important notation. N of A is just the null space of A, which is the solution of the homogeneous system of equations that you can produce using the matrix A. Let me end up with the notion of non-singular matrix. Before doing that, we need to define what is a square matrix, and that is very obvious. Let me just write definition. It's a matrix of dimension n by n. Now we can define non-singular matrix, and here is the definition. Definition: a square matrix A is non-singular if the null space of A is just the set 0, 0, 0, 0. Then this is the definition of a non-singular matrix. And let me just say that if A is not non-singular, it is called a singular matrix. Then we can say in a different way, if the null space of A has infinitely many vectors, then the matrix is singular. And if the null space of a matrix is just the vector 0, 0, 0, 0, that means that the matrix is non-singular. As an example, we just do example. If we think about the matrix A equal to 2, 1, 1, 0, 2, 7, 17, 1, 13, then to decide if it is singular or not singular, we need to compute n of A. And to compute n of A, we can do the reduced echelon form of this matrix, which is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the null space of this matrix is equal to the null space of this matrix, but the null space of this matrix is the solution of the system x1 equals 0, x2 equals 0, x3 equals 0, which means that this matrix, the null space of A, is just the set 0, 0, 0, and that means that this matrix A is non-singular. Let me do another example. If we consider the matrix A equal 1, 2, 2, 4, then in this case we can check that this matrix is row equivalent to the matrix 1, 2, 0, 0, and then the null space of A is just the solution of this system, x1 plus 2, x2 equals 0, and 0 equals 0. And to solve this system, we can say that the basic variables are x1, this is the basic variable, and x2 is the free variable. And then we have that x1 is negative 2x2, and that means that the solution of this system is negative 2x2 and x2, such that x2 is a number. And if we are thinking geometrically, this is a line with direction vector negative 2, 1. But actually, we could have stopped here. When we find a free variable, that means that the null of A is going to have infinitely many elements, and therefore this matrix is singular. Then we can say that A is a singular matrix. Let me just say that, remember that this is the null of A, and it has infinitely many elements. An important observation is that if we define this matrix definition, the matrix I sub n, which is the matrix with a 1 here, 0, 0 everywhere else, a 0, a 1, and then a 0 and 0 everyone else, and then a 1 here. This is an n by n matrix with zeros everywhere else. This matrix is called the identity matrix. Examples are the identity 2 is the matrix 1, 0, 0, 1. The identity 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. Then an easy theorem to show is the following. A matrix A is non-singular if and only if A is row equivalent to the identity matrix. Examples, if we take A, this is an example, equal to 1, 2, 2, 4, then this is row equivalent to 1, 2, 0, 0, and this is the reduced echelon form, and this is not the identity, therefore A is singular. And if we consider A to be the matrix 1, 2, negative 1, 3, we can check that this is row equivalent to the matrix 1, 0, 0, 1, and this is the reduced echelon form, and therefore A is non-singular. Actually, I could have said in this theorem that A is non-singular if its reduced echelon form is the identity matrix. Let me do some connections between what we have learned about functions coming from a matrix. Notice that if we have a matrix of dimension n by n, then we can define a transformation T of A, or a function T of A, from, let's say, Rn into Rm, which is given by this function. V goes to T of A of B equal to A times B. let's see an example. If we have A equal to 2, 1, 4, 3, negative 1, 2, then the transformation here in this case is a function that goes from R3 into R2, and for example, it takes the vector 1, negative 1, 1 into the vector 2, 1, 4, 3, negative 1, 2 times 1, negative 1, 1, which is the vector, we have 2 minus 1 is 1, plus 4 is 5, and here you have 3 plus 1 is 4, plus 2 is 6. Then this transformation takes vectors in R3 into vectors in R2. In general, we have that this matrix will take vectors in Rn into vectors in Rm. Then here we have the vector 0, 0, 0, 0, 0 in Rm. Then by definition, the null space of the matrix is the collection of vectors here in this space that goes into 0, 0, 0. Remember that the definition is the set of vectors V such that AV is 0, 0, 0. Then we are thinking about all the vectors that goes into the vector 0, 0. I forgot to mention that if we have a matrix and I give you a particular vector, for example, if I ask you, is this vector a vector in the null space of A? When you do this, you see that it doesn't go to 0, 0, 0. Then the answer is 1, negative 1, 1 is not an element. We have this. Is not an element in N of A. Let's practice more of this type of questions. For example, is the vector 2, 1 a vector in the null space of this matrix 2, 1, 0, 1, 1, 1? And then essentially what we need to do is to check if 2, 1, 0, 1, 1, 1 times the vector 2, 1, which is the vector 5, 1, 3, is equal to the vector 0, 0, 0. In this case, this is not the case. Then the conclusion is that 2, 1 is not in the null space of this matrix, of the matrix 2, 1, 0, 1, 1, 1. Then to check if a vector is in the null space of a matrix, we just multiply that vector on the right of the matrix, and if we get 0, 0, 0, then it is in the null space. Remember that here we were asking ourselves, is this equal to 0, 0, 0? If it is, then it's in the null space, and if it isn't, it's not in the null space. Then let's continue with this interpretation. The null space of a matrix is the collection of vectors such that the function t of A send those vectors into the vector 0, 0, 0, 0. And if A is a square matrix, if A is an n by n matrix, then A is non-singular if the only vector that goes to the vector 0, 0, 0 is the vector 0, 0, 0. Remember that it's non-singular if the null of A is just the vector 0, 0, 0, 0. Then when a matrix is non-singular, that means that this is the only vector that goes to 0, 0, 0. When we think about this equation, A times B equal to 0, 0, 0, the solution of this equation is the null space of A. But if A is singular, if A is non-singular, then that means that the only solution of this equation is V equals 0, right? If A is non-singular, that means that the null of A is just the set 0, 0, 0, and therefore that means that this equation has a unique solution. Unique solution, because the only solution is 0, 0, 0, 0, as we pointed out here. We have more than that. If we have a square matrix, let me write that down. Theorem: if A equal to Aij is non-singular and B is a vector of the form B1, Bn, then the system A11 x1 plus A1n xn equal to B1, AM1 x1 plus AMN xn equal Bm. This system has a unique solution. Then essentially what I'm saying that when we have that the matrix is a square matrix, then we have a transformation or a function from Rn into Rn. When the matrix is non-singular, that means that this zero vector is the only vector that goes here, right? If the matrix is non-singular. But not only that, if you pick any vector here in the codomain, then there is a unique vector here, let's call it a unique vector x, that goes into that V. Let me do an example of this theorem. Then if we consider the matrix A equal 1, 3, 4, 7, 19, 18, negative 3, 4, 7, then we can check that this matrix is non-singular. How to check that a matrix is non-singular? We just compute the reduced echelon form, and then we can check that the reduced echelon form of this matrix is this matrix, which is the identity. Then, since the reduced echelon form of this matrix is the identity, that means that A is non-singular. And therefore, if we consider the system x1 plus 3x2 plus 4x3 equal pi, 7x1 plus 19x2 plus 18x3 equal square root of 2, and negative 3x1 plus 4x2 plus 7x3 equal to 17. Then we know, because of this theorem, that the solution of this system is unique. Then the solution is going to be exactly a point. There is a point x1, x2, x3. There are values for x1, x2, and x3 that makes this equation true, and there is only one value that makes that true. Please review these questions.